Howdy and welcome back. So binary search tree review. Again, I just want to recap, some of what a binary tree is, then get into what the binary search tree property is and how a binary search tree respects that property. So binary trees. So what was a binary tree? Well, we said a binary tree was a tree composed of nodes who had at most 2 children. So we talked about how our tree structure has some entry points similar to, say, the linked list had. We have a root node. We said how this quickly begins to diverge from a linked list was that at each node, we have the option of stepping left or the option of stepping right. Likewise, each node maintained a pointer to the node that their parent node. We said that the root, because it's that special node, has no parent, but every other node within our tree will have a parent, and they're all some sort of descendants from the root node. We introduced this idea that our nodes are going to store both data. We said in this case of type T1. So again, our binary tree node is going to be a class template here. Then we said that, okay, to make things maybe a little bit easier for considerations, we're also going to have a key, which will be of type T2. And again, the example I provided in the last lesson was, imagine we had a tree of students. Why might we want to organize students in a tree? Well, maybe by the end of the week, you'll begin to see why that is. Definitely by the end of 225, you'll see maybe this utility of that if you're looking to, say, look up a particular student. We said that the key value would be some sort of potentially unique identifier, such as the student's UIN number. That way we could pass in, say, a key to look up some sort of record stored within our tree. Okay, so that was a binary tree. Then we got into this idea of a binary search tree, which was an organized binary tree represented using, in our case here, a linked data structure. We said, as we just communicated, each node is going to contain a key and some sort of data, along with pointers to the node at its left, that at its right, and its parent node. Now we said that if a child or parent node is missing, the respective pointers would be the null pointer. So in the case of, remember these special nodes here, these, oops, let's not do purple, let's do sky blue, whatever color this is. In the case of the leaves, they're going to have no children. We said that our typical node within the tree will have at most 2 children. It could have 1 children, such as this node over here, or again, it could be a leaf with 0 children. We then talked about how in all of these cases in blue, those nodes would have a parent, with the one special case being the root, which again is kind of the node from which all of these other nodes are descendant upon. So in the binary search tree now, the nodes are going to be organized. They're going to be stored in a specific kind of ordering. So they're going to be specifically arranged such that they satisfy what's known as the binary search tree property. So let's assume that X is some sort of node in our BST. Let's say, I don't know, let's go over here and just say this is X. Now the binary search tree property says that if Y is a node on the left subtree of X, so let's say that's Y in this instance, Y's key value is going to be less than that of X's. So if we go ahead and replace these variables with maybe some values, let's say that this node's key is 10. That means that the node to its left must have a key value of less than 10, let's say 8. Now we said that if a Y is in the right subtree of X, then Y is going to have a key value greater than or equal to X. So this could be the case of, say, 15 over here. And notice that this property is going to be maintained at all times within a binary search tree. So if we're inserting into it, which we'll get into a bit later in this week, I believe, we're going to insert such that this property is satisfied. Likewise, if we were to remove a node from this tree, which I'm not sure if we'll get to the remove process this week, and if we don't, you won't see it till 225, but if we do get to it, we'll have to remove a tree such that the binary search tree property is maintained. So with all of that in mind, with that brief, just a bit longer than I suspected. But with that in mind, let's go ahead and move into finding the minimum key value stored within a binary search tree. Then let's talk about an algorithm that will help us determine or find or search for the maximum key value node within our tree. So let's go ahead and get started on those.